I'm Michael Neumann, and I'll be presenting research on structured isosurface mapping of 3D scalar fields with mobile sensor networks out of the Robotic Systems Lab from Santa Clara University. After a quick review of scalar fields, I'll define the research topic for the presentation, describe the multi-layered control architecture we've developed, present simulation results, and finally there will be conclusions and future work. The scalar field is a field where there is a single number associated with every spatial coordinate. Examples of scalar fields include temperature, radiation, pollution concentration, etc. 2D scalar fields can be visualized as a 3D surface where the height of the surface corresponds to the scalar value. Visualizations of 3D scalar fields are trickier. Within scalar fields, there are a number of features of interest that can have practical significance. For instance, a global or local maximum could be the source of a pollutant. A saddle point is a low energy path between minimum. A ridge is a path of optimal service when leaving an RF communication source. A specific level set or contour of radiation level could be used to demarcate a hazardous area. And a minimum may represent a sink. While all of these features are of practical interest, their locations are not always readily apparent. To define them, there are a number of exploration strategies that have been developed. Conventional strategies exhaustively map the region, for instance, by lawn mowing the area. Features of interest like extrema can be easily located once the map is complete. An alternative strategy is adaptive navigation, where the path is chosen based on scalar field information to move towards or along a feature of interest. In our version of adaptive navigation, we use a formation of sensor-equipped robots, creating a mobile sensor network. This path shows a robot formation climbing the estimated gradient to a maximum. There's additional system complexity in that multiple robots need to be working together, but it allows for features of interest to be located quickly and can react better to time-varying scalar fields. So in this presentation, we're going to present the development of a state machine sequencing 3D adaptive navigation capabilities to locate an isosurface of interest and then render that isosurface through periodic contour tracking along the surface. We've developed a multi-layer control architecture for our adaptive navigation work. The lowest level of the architecture is the robot controller, which takes velocity commands for each individual robot and returns state information for the robots, as well as sensed scalar field values. The robot information is fed into the cluster space controller, which manages the group of robots as a full degree of freedom virtual articulating mechanism, whose shape, size, and orientation can be reconfigured during operations. This layer controls the formation using the cluster state data to generate cluster velocities, which are fed into an inverse Jacobian function to generate individual robot velocity commands. Another level higher is the adaptive navigation layer, which uses robot state information and scalar measurements to generate desired formation level movements, which are the cluster space velocities, in order to move toward or along a feature of interest. We've developed a variety of adaptive navigation primitives, such as gradient climbing. The highest level is the state selector layer, which cycles through the appropriate adaptive navigation primitives based on sensed scalar field values in order to perform the user-specified task. So now going into more detail on each level, first our simulations use a model of the AR drone made by Parrot. Ignoring pitch and roll, which autopilot controls, we're left with a 4 degree of freedom system with 3 position variables and a heading. The drone dynamic model equation is in the second bullet, shows that the acceleration of the drone is equal to the difference of the commanded velocities multiplied by a matrix of gains and the actual velocities multiplied by another matrix gains, plus a term representing disturbance due to wind. The gain matrices are diagonal and were experimentally determined by another research group for the Parrot, and the wind term uses the von Karman turbulence model shown in the third bullet. Finally, noise was added to the positioning and scalar field measurements based on characteristics of common off-the-shelf sensors. Our cluster space control layer abstracts formations as fully articulating virtual structures. In this layer, we convert robot space variables like the position and heading of the quadcopter to cluster space variables like the position of the formation centroid, heading of the formation, and distance between pairs of robots. The cluster space variables are used to control the shape and size of the formation, and as well as its velocity. In this work, we've used a proportional controller with static desired shape, size cluster variables, and estimated cluster space state variables by converting from robot space state variables to generate desired cluster space velocities. The desired cluster space velocities are then converted to robot space velocities that are sent as commands to the individual vehicles. For this work, we utilized a 4-robot cluster space definition with the robots arranged in a tetrahedron. For the cluster definition, we developed kinematic transformations to convert between the robot space variables, like the position and heading for each individual robots, and the cluster space variables, which you can see like the L12, the distance between two, and the position of the frame. And we use the kinematic transformations to derive Jacobians to convert between robot space velocities and cluster space velocities. The adaptive navigator determines the desired formation level velocities based on sensed scalar values. The work uses an Isosurface adaptive navigation primitive, which estimates the scalar field gradient based on the values sensed by each quadcopter. Then a velocity is created by 2 terms. One term moving perpendicular to the gradient, causing the formation to orbit around within the isosurface, plus a term that moves up or down the gradient to keep the formation on the desired isosurface. This velocity is then normalized so the formation always travels at a constant specified speed. The state selector layer links together different adaptive navigation controllers to perform complex missions. For example, when performing isosurface mapping, the state selector alternates between complete orbits traveling in the isosurface of the plane and moving set distances along the isosurface. Now we have some simulation results showing the formation of protein in the desired isosurface, and then periodically circumnavigating the isosurface as it moves closer to the source. So you get a sense of where the isosurface is. And here's another simulation result in the left picture. As can be seen in the previous videos, our architecture successfully manages to map isosurfaces. It also has several benefits over the methods currently being used, which is contour tracking in consecutive planes normal to a predefined direction, and is shown by the blue planes in this figure. The method of isosurface mapping, the green planes in the figure, simplifies operation by not requiring a specified vector. It reduces travel and time needed for mapping extended plume-like features, and improves surface interpretation. Plane of the slice to get additional information to the viewer. In conclusion, adaptive navigation is a compelling method for 3-dimensional scalar field exploration. We presented our current work, including a quadcopter model used in simulations, our multi-layered control architecture, and a novel isosurface mapping process verified in simulations. Going forward, we hope to perform experiments of our 3D adaptive navigation techniques, starting with extrema seeking with a formation of 4 quadcopters. We're also exploring ways to adaptively size formations during flight instead of using predefined formation sizes, which this will help us, our distributed sensor network, filter out noise. Finally, another graduate student is exploring swarm solutions to perform similar scale field adaptive navigation tasks. Thank you for listening to my talk, and I'll welcome any questions.